Good morning, friends. Today we are going to deal with respiratory physiology, airflow resistance, hemoglobin, and some abnormalities with the hemoglobin combination with cyanide, with carbon monoxide, and methemoglobinemia, all that stuff. So let's first deal with airflow resistance. There is only two things that I have to discuss about airflow resistance. First thing is that 50% of the resistance of airflow belongs to upper respiratory tract and the rest 50% belongs to lower respiratory tract. And where is the resistance the most and where is the resistance the least? So we know in the respiratory tract we have trachea, we have bronchi, and we have bronchiole, and then terminal bronchiole, right? Respiratory bronchiole, we have alveolar duct, we have sac-like structure, we learned all this, right? Okay. So we know that in bronchi we have hyaline cartilage. So that the air inside bronchi is the most turbulent. So that means there is high resistance. If the flow is very turbulent, there is high resistance. And we know that there is no cartilage in bronchiole. So let's say in terminal bronchiole, we find there is the least resistance. I hope you understand. So this is all about airflow resistance. Next, let's check on to hemoglobin. We know that hemoglobin consists of heme and globin. 4 molecules of heme and 4 molecules of globin. Right? So heme is actually iron plus proto 4,5. Right? And globin, actually there are 4 kinds of globin chains: alpha chain, beta chain, gamma and delta. So these are arranged into 4 molecules or 4 chains or 4 molecules of globin. Let's see. Alpha to beta 2. So totally there is 4. And alpha to gamma 2. Alpha to delta 2. So let's say alpha to beta 2 is HbA. Alpha to gamma 2 is HbF. Alpha to delta 2 is HbA2. Okay? This is a different hemoglobins. It is hemoglobin A, hemoglobin F, hemoglobin A2. We name it according to difference in their globin chains. Understood? So HbF here, F denotes fetal. So it is found in fetus. So in fetus we know that the lung is not functional, right? So we need hemoglobin more affinity. The hemoglobin should be more affinity towards oxygen, right? So HbF has more affinity towards oxygen than HbA and HbA2. Understood? Also, we need to know that myoglobin, we know that myoglobin binds with oxygen, but not like hemoglobin, only one oxygen it binds. Myoglobin binds with only one oxygen. But thing is that myoglobin has more affinity towards oxygen than hemoglobin. Understood? I hope you understand. So these are the important stuff about hemoglobin. Now we have to learn about hemoglobin dissociation curve. So let's check into that. So let's say hemoglobin is found in 2 forms. Hemoglobin being committed with oxygen and single hemoglobin. Sometimes hemoglobin has a relationship with oxygen and sometimes it's single. So say who will be in a relaxed form, single or committed? So most people will say single people are more relaxed. So this form is known as a relaxed form. A relaxed form. Hemoglobin being single is in relaxed form, and hemoglobin associated with the oxygen is in taut form. I hope you understand, right? Hemoglobin associated with oxygen is in taut form, and hemoglobin single is called relaxed form. And where do we find a relaxed form of hemoglobin? When do we want oxygen to be released from hemoglobin? And tissues. We need oxygen in tissues, right? And carbon dioxide is being secreted. We need oxygen for the tissues to take place, utilize the energy, right? Okay. So oxygen release is seen, a relaxed form of hemoglobin is seen in tissues. And where do we find hemoglobin associated with the oxygen? We find it in the lungs, right? Because oxygen is lot and hemoglobin binds with oxygen and come to tissues, release it and become relaxed. Okay, that's there. Now now we have to plot this graph for hemoglobin dissociation curve. Let's say here it is percentage saturation of hemoglobin. That means how much hemoglobin from the total amount of hemoglobin is bound to oxygen, right? And here we denote PaO2, that is partial pressure of oxygen, and we give it represent it with mmHg. Okay, so the graph is sigma shaped, S-shaped curve. So this is the graph. That means there is some relativity, or there is a relation that makes it curve like an S shape, right? Why is it in the shape? Why can't it be a straight line or something, like myoglobin? Myoglobin's curve is like something like this. So why don't we have a curve like that? First of all, we know that myoglobin has more affinity towards oxygen than hemoglobin, right? And one more thing is that hemoglobin, when he is committed with oxygen, will make other hemoglobin to be committed. Something like that. And hemoglobin who are, single will make other hemoglobins, tendency to become single. That's what everybody does, right? If someone is someone are committed, they want everybody to be committed. And someone is single, they want everybody to be single. So there is a property called allosteric effect. Hemoglobin is an allosteric structure. So this relation is known as cooperativity. So that's the important thing to remember. Now we will learn about shift of this oxygen dissociation curve. So it can be shifted towards right and towards left. Any way is possible, right? Okay. So when it will be shifted towards right or when it will be shifted towards left? Let's see. If the curve is shifted towards right, that means more partial pressure of oxygen is required to reach that certain percentage of hemoglobin saturation with oxygen. Understood? Because before, if the oxygen concentration was like 50, the hemoglobin will be bound to let's say 70%. But now to reach this 70% of hemoglobin saturation, we require maybe 80 mmHg of oxygen. So that means the requirement of oxygen partial pressure is increased to reach that same percent saturation of hemoglobin. Understood? Right. That's when this curve is shifted towards right. So when is this curve shifted towards right? At tissue. At tissue level, we want hemoglobin releasing oxygen, right? So hemoglobin's affinity to oxygen is reduced when it's shifted towards, towards right side. Because more oxygen should be available to bind to hemoglobin. That means hemoglobin is not ready to take up oxygen, right? It's releasing the oxygens. So when is this hemoglobin releasing oxygen takes place? In tissues. So it happens at tissue, and there are some friends of hemoglobin. They are carbon dioxide, H plus, 2,3 BPG, and temperature. These guys, these four people, carbon dioxide, H plus, 2,3 BPG and temperature. These people are very good friends of hemoglobin. They say, come on hemoglobin, don't bind with oxygen, let's be relaxed. This is what carbon dioxide, H plus, 2,3 BPG and temperature says. So this helps in reducing the hemoglobin's affinity towards oxygen and making hemoglobin release oxygen, and it happens in tissues. So all these things will be higher, high carbon dioxide, high H plus, high 2,3 BPG and temperature at tissue, and oxygen release is happening there. And tell me, where will leftward shift of hemoglobin dissociation curve will happen? At lungs, obviously, because hemoglobin has more tendency towards oxygen. Less partial pressure is required to make the same percent saturation of hemoglobin towards oxygen. So that means those friends are not there at lungs. Those friends are situated at tissues and not at lungs. So there is less carbon dioxide, less H plus, less 2,3 BPG, and less temperature. I hope you understand. It's very easy to understand, right? We know carbon dioxide, H plus and temperature. Let's see what 2,3 BPG actually is. So we have learned this shift, right? Now let's check into 2,3 BPG. So we know in the glycolysis we have an intermediate compound called 1,3 BPG. There is glycolysis happening, and we know that in that middle there is an intermediate called 1,3 BPG. And this 1,3 BPG can be converted, transformed into 2,3 BPG by some kind of mutase. It is transforming 1,3 BPG to 2,3 BPG. Understand? So less energy is found, but thing is that this 2,3 BPG is helping in the release of oxygen from hemoglobin. Also, along with carbon dioxide, H plus and temperature, this 2,3 BPG is also helping in release of oxygen, and it is present at tissues. It is more at tissues. Understood? So that's there. Now we have to deal with some problems of hemoglobin. Let's see. So we have learned that hemoglobin has heme and globin. If there is some abnormality towards globin chain, let's say if there is a problem with alpha chain, it results into alpha thalassemia. If there is a problem towards beta chain, it will result into beta thalassemia. Also, there is another problem called sickle cell anemia. know all these things. We have learned it in plus 2 and all, right? So there is globin abnormality causing alpha thalassemia, beta thalassemia, sickle cell anemia. So we have learned hemoglobin, which is found to have heme and globin, and we have learned 3 abnormalities related to globin: alpha thalassemia, beta thalassemia, and sickle cell anemia. Now we are going to check with heme. Heme has iron and protoporphyrin, right? Okay. So there are 3 things. One is carbon monoxide poisoning, and there is methemoglobinemia, which is actually Fe2 plus is converted to Fe3 plus, and there is cyanide poisoning. There is 3 things, and we have to look into. Carbon monoxide poisoning, Fe2 plus converting to Fe3 plus is called methemoglobinemia, and cyanide poisoning. So let's check into each one. First of all, carbon monoxide poisoning. If carbon monoxide is bound with hemoglobin, actually carbon monoxide has the hemoglobin has more tendency, more affinity towards carbon monoxide than oxygen. So there is a competition between oxygen and carbon monoxide to bind with hemoglobin, and guess who wins? Carbon monoxide, because actually it is 240 times more affinity. There is 240 times more affinity towards carbon monoxide than oxygen. Understood? So therefore, carbon monoxide wins in the battle. So what do? We increase the number of oxygen for treatment. We give more oxygen, right? So that's there. And the other thing is that if there is a competition, one thing, and the other thing is that carbon monoxide when bound with hemoglobin, see, hemoglobin is there, it's bound with carbon monoxide, and if there is oxygen molecules with hemoglobin, this carbon monoxide is not allowing the oxygen molecule to be released. It is hugging all that oxygen molecule with each other. So therefore oxygen molecule is not available to the tissues, right? It's not giving to the tissues. So actually that happens, that is called allosteric modification. This process is called allosteric modification of hemoglobin by the carbon monoxide, right? Okay. And one more thing that we have to know, so there is one, we learnt there is competition between carbon monoxide and oxygen is not able to be released. It's called allosteric modification. Other thing is that it causes a cherry red lips. It causes cherry red lips. But don't go and get carbon monoxide to convert your lips into cherry red thingy, because it's not that good. Anyway, hemoglobin, carbon monoxide provide a competition towards oxygen and also not allowing oxygen release, right? So actually hemoglobin is there, but the thing is that those hemoglobin becomes useless. So therefore there is a functional anemia there. Understood? So carbon monoxide poisoning causes functional anemia. I hope you understand. It's very easy to understand, right? Hemoglobin is there, but it's useless. Those hemoglobin. So let's see. It's equal to less hemoglobin. That means it is equal to functional anemia. Understood? Now it is methemoglobinemia. That is Fe2 plus is converted to Fe3 plus. And why it is converted to Fe3 plus? By some drugs. What are those drugs? One is benzocaine, lidocaine. Those are local anesthetics, right? The other one is nitric oxide, and the other one is dapsone. You know, dapsone is an antibiotic, nitric oxide is a vasodilator, and benzocaine and lidocaine are local anesthetics. These drugs will convert Fe2 plus to Fe3 plus, thus resulting into methemoglobinemia. And if there is methemoglobinemia, we said in carbon monoxide poisoning, we have cherry red lips. If it is methemoglobinemia, we have chocolate colored blood. Understood? So methemoglobin is actually a toxic thing, and if it is bound, if it is converted to Fe3 plus, now this Fe3 plus is not able to bind with oxygen. So actually that hemoglobin is also being useless, right? Yeah. And one more thing is that if it is bound, if it is converted to Fe3 plus, oxygen which is binded with other hemoglobins are not able to be released. So same thing with the carbon monoxide, the same thing is happening with methemoglobinemia also. And one more thing that we have to know is that the treatment method of methemoglobinemia. The treatment method is methylene blue. It is methylene blue. Understood? So we give methylene blue to convert back into Fe2+. Very easy to understand. Now we are going to deal with cyanide poisoning. Then one more thing that I have forgot to mention in carbon monoxide is that it's a percentage of carbon monoxide which is poisonous. Actually, normally there will be 3%. 3% is found normally, and if it is 10 to 15%, that means this guy is smoking. But if it is more than 15%, that means it is poisonous. Carbon monoxide. Okay. Now we understood both carbon monoxide poisoning and methemoglobinemia. Now we are going to deal with cyanide poisoning. What is cyanide poisoning? Actually, cyanide is dealing with mitochondria. It is blocking, it is binding with Fe3 plus in the electron transport chain and blocking the electron transport chain. In the end of the electron transport chain, oxygen is receiving that thing, right? The electron. But thing is that when Fe3 plus is bind with cyanide, it blocks this electron transport chain. Therefore, it blocks aerobic respiration. It blocks aerobic respiration. Therefore, it undergoes anaerobic respiration, anaerobic metabolism. When it is undergoing anaerobic metabolism, it results into formation of lactic acid. Therefore, it causes lactic acidosis. It causes lactic acidosis. Understood? Very easy. Now, if it is causing lactic acidosis and all this thing, we know that the oxygen it's almost equal to no oxygen, right? No oxygen to its tissue, because that oxygen is not able to do its duty. So therefore it's just equal to no oxygen. That means it causes what? Functional hypoxia. So functional anemia, carbon monoxide. Functional hypoxia, cyanide poisoning. What is hypoxia and hypoxemia is different? Hypoxemia means there is no oxygen in the blood, but actually there is oxygen in the blood. But hypoxia means there is no oxygen in the tissue. That is hypoxia. Okay. Now you understood the stuff. So functional hypoxia is caused by cyanide poisoning, right? So what is the treatment method for cyanide poisoning? So there is one thing: move the cyanide from mitochondria. Move away this cyanide from mitochondria. How can we do that? We can convert the hemoglobin's Fe2 plus to Fe3 plus, because cyanide is binding with Fe3 plus. We have to convert the Fe3 plus, Fe2 plus in hemoglobin to Fe3 plus by nitrate, amyl nitrate. We use amyl nitrate for that. Okay, we convert Fe2 plus to Fe3 plus. So cyanide binds with that. So we have, but the thing is that when we are converting Fe2 plus to Fe3 plus by amyl nitrate, we have methemoglobin, which is actually toxic, right? Okay. That's a disadvantage of using amyl nitrate. Now other thing is, other treatment method. One is amyl nitrate, amyl nitrate, and the other one is hydroxycobalamin, hydroxycobalamin. And now the third one is thiosulfide. If you are using hydroxycobalamin, we know it is a vitamin B12, right? So if we are using hydroxycobalamin, we form cyanocobalamin, and which is excreted through urine. And thiosulfate is there. If we are using it with cyanide binds with thiosulfate, forming thiocyanate, which is excreted through urine. Both of these are excreted through urine. Okay. Now cyanide poisoning is also over. Next class we will be dealing with pulmonary circulation in the next video. So thank you all for listening. If there is anything that you need to tell me, please do contact me in my Instagram. I'm putting down my Instagram down here below in the description box. And also I'm putting down my WhatsApp number. Please do contact me if there is any mistakes in the portions that I have taken, and if there is any suggestions also. And I hope you will understand what I'm trying to teach. Okay, thank you all. Bye.